Ah. Okay, well.
Ding, ding, ding.
And then there's sort of,
Conversation.
yeah,
Conversation.
yeah, okay. Okay, so maybe let's start now. Okay. So today I want to think about what sort of the distribution of random solutions of these different random constraint satisfaction problems, and think of them as sort of a spin system or Markov random field on the graph that we're interested in. So imagine k colorings of a graph. So remember, we want to assign one of k values to each of the vertices, and we want neighboring vertices to be different. So we could think of we could write a uniformly random coloring. Oh, the probability of that, well, it's just, it's just the uniform distribution of indicator that that it is a coloring. But I could write it as just 1 over the total number of colorings, and then write the indicator as sort of the condition of each of the constraints, sort of product over all u next to v of indicator sigma u is not equal to sigma v. Okay. If I was looking at independent sets, and I wanted a random independent set, I could also write it in a sort of similar product form. So v. So this will be taking values 0 and 1 on each of the vertices. And now I want, at least one of each neighboring pair to be 0. This will give me the uniform distribution on independent sets, but I'm going to be interested in big independent, the larger ones. So I might want to sort of tilt the distribution towards independent sets that are sort of bigger. So you could add in another parameter, lambda sigma u. So lambda is just a constant. It's the fugacity. And this is called the hardcore model. And it's a weighted distribution over independent sets. And again, it has sort of this product structure. So it's sort of product over terms on the edges and also ones on the vertices. And these are sort of special cases of a sort of much more general sort of system of distributions that I'll call a spin system. And sigma will just take some values in some finite set x to the v. And the probability, there'll be a normalizing constant, and then some kind of interaction between the values on edges and then some kind of just value for the values on particular vertices. And so it will be defined in terms of the values it takes on each vertex, and these functions psi and psi bar. And this one lives on the edges, and this one lives on the vertices. Now, in most of the examples I'm going to look at, these will just be the same for every edge and the same for every vertex, but sometimes it's useful to have more generality. Okay, and so lots of things fit into this class. Models you've probably, or many of you will have seen, like the easing model would be, you have a +1 and a -1 on each vertex. And sigma u, sigma v. So this is, I guess, originally a model of kind of magnetic systems, and each vertex is either in a +1 or -1 state, and the distribution is biased towards having, so this sum of sigma u, sigma v is sort of, you get 1 here if sigma u equals sigma v, and -1 if they're not equal. And so it's sort of, so at least if beta is positive, this is biased towards having more pluses next to pluses and more minuses next to minuses. And so this was with 2 states for each one. Another one is the Potts model, where it's sort of generalizing this to k states rather than just 2. Okay. And of course, in the first example, I didn't write it in the form of this, but of course we could, instead of had product over uv outside of e to the beta sigma u, sigma v. And for the Potts one, we'll do it the same way, except I'll write e to the beta indicator sigma u equals sigma v. So again, it's sort of biased towards having pairs that are equal. These are, the easing model is a special case of the Potts model, except there's some sort of, you have to sort of slightly reparameterize beta with a factor of 2. In the case of beta equals -infinity, then this is just, well, okay. So, no, yeah, okay. Yeah, so if beta equals -infinity, we get a 1 here if they're not equal, 0 here if they're equal. So this is just the coloring model. Okay, so this is, okay. So why do I want to care about these models? Well, they have nice condition. Well, first of all, it will be, we'll want to understand things like random colorings on, the different random graph models, and these spin systems have nice sort of conditional independence properties. So the Markov random field property let's say that if I have, okay, a set A in a set V, and I'll write partial A to be sort of the outer boundary of it, so the vertices that are outside of A but next to it. So when V, distance from U to A equals 1. So if I look at the probability that our random configuration or our random coloring, say, takes some value in A given its value in the rest of the graph. So this will just be, so if I specify the coloring everywhere else, then the distribution here should just be a uniform coloring, provided you don't sort of violate any of the edges between A and A complement. So it should really only depend on what's happening on the boundary. And indeed, this is the case. So XA. So in order to understand what's the effect of the configuration in the rest of the graph, it's enough just to know what's the values on the boundary of A. And this is true for any of these spin systems, in just colorings. And basically it comes from taking this product form, and we can sort of, it factorizes into terms that are, okay, product of U in partial A sigma U product of U and V in partial A. So the part of the product that just depends on things in partial A, and then a product of things that are just in A, psi bar U in things that are edges that are in A, or one end is in A and the other end is in either A or partial A, or the boundary. Sigma U, sigma V. And then the same thing again for a complement minus partial A of U in a complement minus, I think I've gone below the line of what you can see, which sigma U, sigma V. But basically, so basically I want to break up the vertices and edges in this product into the ones that only involve the boundary, the ones that only involve A and maybe edges from A to the boundary, and the ones that only involve a complement minus partial A and their edges to partial A as well. And these factorize. So it says what's happening in, so the value inside A and the value inside A minus partial A complement are conditionally independent given the values on the boundary that splits them into two. And actually this would be true for any, if rather than having the boundary, I just took any set S that separates A from B, so that there's no edges going from A to B. So the configuration or the coloring on S given that the coloring on A and the coloring on B are conditionally independent. Okay. Sorry, that was a very...
without partially complement is empty, right? It should be
yeah, this, I mean,
V.
I think I mean, A complement minus partial A. Yeah. Okay, good. Any other errors or questions? Okay, so this, okay, so you know this definition is for a finite graph, but I might be interested in extending these to infinite graphs in order to take some sort of appropriate limit, but this wouldn't really make sense if our graph was infinite, because you know, like the number of colorings would be infinite, say, on an infinite graph, or it could be, yeah. I mean, it could also be 0, but it's so in general, I can't just make sense of this formula on an infinite graph. So how should we extend it from a finite graph to an infinite graph? And the idea will be in terms of measures that satisfy this formula. So
what's the motivation for considering infinite graphs?
Okay, so we'll be thinking about this on a random graph. And random graphs are kind of, you know, locally, as we saw yesterday, they're sort of pretty simple. They look like trees. But sort of eventually they have long cycles and they have some sort of complicated long-range structure. But I want to sort of take a limit of the local behavior. And so the limit of that will be an infinite tree. And so I want to define sort of how something like a random coloring or these different other models behave on infinite trees. And a lot of the predictions we have for these random constraint satisfaction problems will be in terms of understanding the measures that we get on the sort of limiting object on the infinite tree. So that's sort of the direction we're going in. Yeah. So, okay. Maybe I shouldn't have started writing before it was dry. It's sort of a bit. Is there a trick to? Anyway.
Fight wet with wet.
Okay. Get a.
That's your only dry cloth. Okay.
Okay. So that was a bit too wet, I guess. I guess from the pandemic, I'm out of practice using blackboards. But, okay, so okay, maybe I'll. So on a sort of infinite graph, graph G, we'll say a measure mu satisfies the spin system psi bar. If for all A finite, star holds, where star is this equation. And I think I want to add in like locally finite here. So, you know, all of the degrees will be finite, and otherwise we'll get into various issues, but and probability of sigma A equals partial A. Well, this is now something that just depends on a finite set of vertices, A and its boundary. So it will just be, given by the finite formula. So A partial A. Okay, so within each sort of local neighborhood, once we fix the boundary, it looks like the coloring model or the easing model. Then we'll say that this is sort of a then mu is a Gibbs measure. And basically just a way of extending this sort of spin system we defined on finite graphs to one on infinite graphs. Now classically, you would study this on lattices usually. So there are Smirnov and just last week Hugo Dominil-Copin won Fields medals in part from understanding the easing model on 2- and 3-dimensional lattices and also the Potts model. So, but from the point of view of random constraint satisfaction problems, the objects we'll be interested in will be where the graph is a tree. Okay. Oh yeah, and I forgot to mention this sort of conditional.
There's some confusion about where mu appears in this form.
Oh yeah. I'm probably going to randomly swap between p and mu at different points. So and apologies for the. Yeah. So okay. So one more thought that I should have said about this. Just this conditional independence property. If we have a finite tree, and I tell you the value of the root, then the root separates all of the subtrees from each other. So conditional on the root, the subtrees are conditionally independent. So trees have, unlike other graphs, trees, it's very easy to find a separating set that splits the graph into parts. So it's really the conditional independence you get from this property that's going to make a lot of calculations tractable. You need, on like the 2-dimensional lattice, say, to work out the correlation between pairs of vertices, you need some very deep mathematics. On a tree, it will be very simple to work out terms like that. Okay, so I have this definition for infinite graphs, but of course you could say, are there actually anything that satisfy that? And there basically always are. Yeah.
Interpret that like a marginal on a complement, which is infinite, but
Yeah. So if I
guess my doubt arises from the partition function, the normalization constant. I mean, it's
so this is really just the Yeah. So if I have an infinite graph, then this partition function may be infinite. But here, I'm only summing over configurations on A and its boundary, which is a finite set. So here, ZA was, so actually this normalizing constant should have also included the configuration on, so it should really be A x partial A, so it will depend on the values that I put on the boundary here. And then it's just a sum of configurations on A of this. So
the definition doesn't seem quite correct, right? The conditional distribution should be given everything outside A. The right-hand side only depends on the boundary of A, but to actually define a Gibbs measure, you would have to assume it's Markov, right? So
oh yeah, so
it should be mu of sigma A equals XA given sigma A complement equals XA complement equals the right-hand side, which happens only to depend on the boundary of A.
yeah, so I wanted to say, so it has this property if this holds, and this conditional probability is given by that formula. Yeah. But yeah, I mean, maybe it would have been smarter to write this as, given sigma A complement equals XA complement, and then you see that the probability just depends on the value on the boundary. Okay, good. So so can we actually find such a measure? Well, I mean, it could be that I can find you infinite graphs on which there's no way to sort of have any valid configurations on it. So I need to make some sort of assumption. One is, I could ask that it's permissive, which will basically mean that I can, for any vertex u, and any configuration on sort of the neighbors of u, there exists a state such that product of psi of w in partial u xw is greater than 0. So there's some, so if I have a vertex and I tell you the labels of each of its neighbors, there's at least one valid way of filling in the vertex. So in the coloring model, this will only be the case if the number of colors is at least as big as 1 plus the maximum degree. In that, yeah.
Does this definition imply that you can always construct these infinite graphs by taking boxes to infinity?
Yes, that's the next thing we want to do. Yeah, indeed.
So this condition basically asserts that ZAs are not 0, right?
Yes. Yeah, exactly. So for any set A, ZA will always be 0. ZA, and any choice of boundary condition as well is always greater than 0. Okay. And so then, we'll do exactly the sort of construction that was suggested, which was, so if I could take a sequence of finite sets AN that are increasing to the whole graph, and a sequence of boundary conditions on on these ANs. And okay, and let's say A is a subset of all of these. So I'd like to define the distribution of mu of sigma of A given X as, you know, the probability in the finite graph of sigma A given partial A n equals X partial A n. So I have some infinite graph. A is the vertex or is some set at the top here. AN is some bigger set. And I want, and then I set a boundary condition along here. Then I have a formula for the distribution inside this set. And I can look at what's the distribution of A. And what I'd like to hope is that if n tends to infinity, then that will converge in distribution. But it might not. But we could at least find some subsequence on which it converges. And I could, okay, so this is for some fixed A, and then for bigger A's, I could find some further subsequence of that, and I could use a diagonalization argument to sort of take a weak limit along some subsequence of these ANs and their boundary conditions, and such that that converges to some Gibbs measure mu, and mu will satisfy the Markov random field property, and well, be a Gibbs measure. Okay, so essentially the proof of existence is a weak limit along a subsequence. So and as long as the model is permissive, we'll always be able to find such a subsequence. On the other hand, you could ask, well, yes?
So if it's just along a subsequence, will you be able to say anything? Like, can you actually understand what this limit is? If it's like, maybe if you chose another one, it would be different. Is that an obstacle?
Very good. So there's a couple of questions you could ask. So we know that it exists. You can ask, is it unique? And the answer is, depends on the spin system. So roughly speaking, what we'll see is that if the interactions between neighboring vertices are kind of weak, like the trivial spin system would have no interactions between neighbors, and then just everything would be independent. And then then whatever boundary condition you set, you'd always get the same distribution in A. And so then in the limit, there could only be one limit, which is just everything IID. Now, with, say, the Ising model, if beta is small, the parameter of that was small enough, then this would still be the case. The boundary would have a very small effect on the top, and we'll prove that in a moment. But on the other hand, if the interactions were very strong, you might have, it may be that even a very distant boundary condition affects what's happening at the top of the graph, and we'll sort of, and this is one of the things that we're moving towards trying to understand. So how distant boundary conditions affect the value at, say, the root of the tree.
Can you actually understand what happens when you don't have uniqueness of this limit, or is it some kind of thing that you want to rule out and then not think about it?
No. So the interesting sort of regimes for random constraint satisfaction problems there'll be multiple limits. And part of the theory involves sort of understanding which of those limits is the one that you should be looking at. So if there's sort of, so we talked yesterday about what is the local weak limit of a graph, which is like picking a random vertex and looking at the configuration around it. But I could talk about the local weak limit of a graph with a spin system on it, and the limit of that would be, you know, some limiting graph decorated with, say, the easing model or the coloring model, and with some distribution. And but if there's multiple Gibbs measures on the limiting graph, then, you know, you have to somehow understand what is the right one to study. And well, we'll sort of move towards seeing how to do that. Good. Any other questions? Okay. Right. So, yeah. If our graphs were lattices, to show non-uniqueness of, say, in the easing model, there's a famous argument called the Pious Argument, where you sort of say if all the boundary conditions were plus, then it's sort of very unlikely to find a large sort of bubble of minuses here. And so essentially, in the easing model, when beta is large, basically it should look like everything being plus, but just a few small islands of minuses. In the case of trees, we'll be able to compute the thresholds in a much easier way. So let me take a moment to sort of see how we can, say, compute marginal distributions for you know, spin systems on trees. And so we'll switch back to finite graphs for a moment.
Sorry, can I ask you
Yeah.
a question? In your formulation, is like to know the information, it suffices to know the frontier.
Yeah.
It can be formulated in information terms, this property, this Markov random, like with entropy or something like that?
So, okay. So when we look at a tree and our spin system on it, there's sort of, there's actually two interesting thresholds that can come up. So let's say we're looking at the easing model. Or one is, I ask, is there a boundary condition here that's a long way away that kind of affects the marginal probability at the root? So this is sort of taking a worst case boundary condition. Another one would be to sort of take your Gibbs measure, take a particular Gibbs measure, look at the random values you get on, say, level n, and then ask, given that, can I guess the value at the root? Or does the mutual information between the root and level n tend to 0, or is it bounded away from 0? This second notion is one that we'll talk about in a couple of lectures' time. And I think that's maybe more closer to the information theoretic or notion that you're looking for. From the point of view of existence of, or uniqueness or multiple Gibbs measures, it will be more a question of, can we choose some boundary condition that sort of affects the marginal at the root? Yeah. So let's say our graph is a tree, a finite one. And so ZT will be its partition function. And I can take any tree and sort of, let's say, choose some vertex that I'll call the root. And then it will have some children and subtrees hanging off that. And I'll write their partition functions as ZTI. And I want to understand how you go from the ZTI to ZT. And so let me write ZT of A as just ZT times the probability that the root equals A, which is the same as summing over all configurations on all of the vertices except the root, and setting, or let's just say all configurations such that the root is equal to A, and then product of XU, XV. So I'm just looking at the contribution where the root is in some particular state. Okay. So I can write ZTA as summing over the contributions from choosing, let's call these U1 up to UD. So summing over the possible values for the children of so I have a product of ZTI AI, and then the contribution from these edges and this vertex. So psi hat of A D of psi AI with A. Okay, and then this is the effect of each of the edges from the root to its children, and this is the contribution I get from making the root A, and I could sort of rewrite this as psi bar of A D. So move this sum inside the product. I have the sum of AI, psi of A, AI. ZTA AI. And well, each of these ZTI AI, this is the contribution to the partition function in TI of the root being AI, but I could just write this as ZTI times the probability that that particular state is in, or that particular tree is in AI. So product of ZTI times probability. Now, this is probability taken just in the tree TI, that sigma UI equals AI. Yes?
Sorry, I just missed the information. So D is the number of subtrees
Yeah.
coming from the root?
Yes. Good. Any other questions?
What's the difference between PTI and just probability that SUI is sigma UI is AI?
The difference is that the marginal probability in the graph, say T1 of UI or U1 might be different to the marginal probability in the tree T. So it may be that, yeah, you could just have this vertex might have a different probability, this one. In the case of colorings, there will be no difference. But say if we were looking at independent sets, if you have a vertex with bigger degree, then it's sort of harder for it to be in the independent set. So the probability might be higher in this one than in this one. So we need to so it will be dependent on the graph. Okay. And so ZT would just be the sum over all choices of A of this formula. And then okay. So then if I want to calculate the marginal at the root in the tree T, it will be ZT of A over, so it will be just the fraction of the partition function. So ZT over Z, which is basically this formula divided by it replacing A with all the possible choices. So pi bar. AI. So U equals AI. So A prime. Okay. So this gives us a way of calculating the marginal, the marginal probabilities. And this is something you could do with dynamic programming on the tree. So if you want to, say you want to, okay, we'll do a simple example. Say we have just a depth 1 tree. Well, you could first work out what the marginals of each of the leaves are if they weren't connected to anything. And that would just be, well, no. What's the probability that a particular vertex U that's completely isolated is in a state A? Well, then the formula, there's only one term in the formula. So in the graph that's just U, the probability that sigma U equals A is just psi tilde of A over psi tilde of A. So you can work out the marginal probabilities in each of these vertices, and then from that add in the next level of edges and work out the marginal probability here. So you could, and then if it's a bigger tree, you just start from the leaves and work up. Another way of writing that is in terms of what's called belief propagation. this is what's called a message passing algorithm. And so we define the message from a vertex u to a neighboring vertex v. So let's say u is here and v is here. And the interpretation of the message from u to v is that u is saying, okay, if we just consider the graph on my side of the graph, what is my marginal probability? So it's the message from u to v of A is the probability in the graph T minus the edge uv, that sigma u equals A. And then this recursive formula is saying that, okay, so if we have a vertex u and a neighbor v, and then I can work out the message from u to v in terms of the messages from all the other neighbors of u coming into u. So the message from u to v A is equal to psi of A product over partial u minus v sum of AU psi of AUA And this is the definition of the belief propagation function of applied to m, all of the w's into u, w in partial u minus v. So this is a definition.
Supposed to be a line, or
yes, yes.
And then I think on the top fraction on the denominator, you wanted the psi bar of A prime.
I did, yes. Yeah, sorry. This is just supposed to be the sum of A prime, or replacing the numerator where we have A, replacing it with A prime. Okay. And so these are the belief propagation equations, that the outgoing message is equal to BP of the incoming messages. And yeah, and so what I was trying to describing very badly before was that, okay, we know if we have a tree, if you have a leaf in the tree, there's no incoming messages. So there's if u is a leaf, the message from u to v is the belief propagation applied to sort of the empty set. So there's no products here, and we just get psi bar of A over psi bar of A prime. So okay, so you can work out for all of the leaves, I can work out what the outgoing messages are. Now, if I know all of the messages from the leaves to their parents, then for each vertex in the next row, I could work out what its message going up is as a function of the ones coming from its children. So with the BP equations, I can sort of work from the leaves and work out all of the upward messages in the tree, all the way up to the root. And so in that way, I could calculate the marginal probability at the root. And then I could also, once I've gotten all the way to the root, I could start working out all the downward messages as well, where if U is the root and V is a child, then I just need all the other upgoing messages into U to work out the downward one from U to V. And so once I've gone from the bottom to the top, I can go back from the top to the bottom and work out on every directed edge in the graph this set of messages. Yeah.
I think the matrix W has to be AW.
These should be W.
So the MW to U should A should be.
This should be MW to U.
This should be AW.
This should indeed, yes, absolutely, and this should have been AW as well. Sorry about that. Yeah, good. Okay, and so this is something that you can do in linear time. If you have a tree of size n, you can work out all of the marginals in time order n, which is not something you can do on you know, like a general graph. So for a general graph of size n, it's NP hard to calculate all of the marginals.
Linear in what? I mean, there are exponentially many vertices in this tree.
Linear in the number of vertices. So indeed, yeah, certainly not. Yeah, right. Now, if it were, you know, symmetric, then like a balanced tree, then it would be linear in the depth as well. But yeah, no. So I'm just saying that linear in the time in the number of vertices. On a general graph, even linear, you know, you can't. You know, it's likely to be exponential in the number of vertices. So, yeah.
In a general graph, besides computational issues, if there is a loop or something like that, would it cause a problem for?
Yes. So, yeah. So in this formula, we were. I mean, it was coming from this calculation, and this was sort of explicitly using or implicitly using the fact that once I fix the state at the root, then what's happening in each of the subtrees is conditionally independent. Now, once you have loops in the graph, that's no longer the case. So in general, the belief propagation equations you know, won't hold on a sort of general graph. This only applies to trees. On the other hand, we're going to see that at least some of the time, one can sort of take our random graph, say, you know, there are lots of loops, but those are very long. Locally, it looks like a tree. Maybe we can still write down these equations. And actually, you know, and we could even write down this set of equations without sort of thinking or thinking, you know, maybe it has nothing to do with the marginal probabilities. This is just some set of equations or some set of constraints. So this itself is a random constraint satisfaction problem. And it turns out looking for like solutions to random constraint satisfaction problems of this form can help us with our original ones. And okay, the direction I'm going to go in is that, you know, I said on the first day that when we have a random constraint satisfaction problem, or a lot of the ones I was interested in, at some point they split into lots of clusters of solutions. And really we want to count not the solutions themselves, but the clusters of solutions. And the clusters, it turns out, at least in the cases that I'm going to talk about, can be encoded as solutions of belief propagation equations. So the clusters themselves are given by a different, more complicated random constraint satisfaction problem, which makes it sound worse, but we'll be able to sort of essentially just calculate the expected number of solutions of this set of equation, at least with some restriction on the set of m's that we look at, and from that deduce how many clusters there are. And basically the point at which we run out of clusters of solutions will be the same point at which we run out of solutions in total. So that's the sort of broad arc of where we're going with this. So it's to take this nice formula that works very nicely on trees. We can calculate anything we want on trees with it. And then pretend that it still works on graphs, but interpret it as a way of thinking about a cluster of solutions. And I'll sort of tell you why that's a reasonable sort of thing to think in a couple of lectures' time. Okay, but for now, I haven't completely run out of time yet. I want to actually do a few calculations with these. So what would the BP messages look like when, for say the easing model or the hardcore model? So for the hardcore model, remember this is the one for independent sets. Then, okay, the messages are just, so M is, you know, the state space is just 0 or 1. So it's enough to just sort of look at what the message from U to V of 1. And, well, the psi bar of 1 is lambda. And we only get a contribution. And since 1s can only be next to 0s, we'll just get product of m from W into U of 0. And on the other hand, the corresponding value for 0 will just be a +1. For the easing model, +1, product over W, e to the beta minus over the same thing plus essentially the same product except with the plus and the minus switched around. M minus beta M plus. Yes?
Sorry, where does the 1 come from?
The 1, okay. So for the hardcore model, our functions were psi tilde is equal to lambda to the x, and psi of xy equals indicator that of xy equals 0. So, so this lambda is psi tilde of 1 times, well, we'll only get a contribution when we have, so if x equals 1, we only get a contribution when y equals 0. So we get the message, the 0 message. If we let x equal 0, then psi tilde of x is 1, and psi of 0y is always 1. So we get a 1 times the product of 1s for this term. And in the Ising model, we get, if we put a plus here, we get e to the beta m plus e to the minus beta m of minus, product over all the neighboring vertices, and then the denominator, the same thing, plus switching pluses and minuses. Okay. So far I've been sort of defining these on finite graphs, and then the message on each edge might be different. Suppose we have a set of messages satisfying the BP equations on an infinite tree. Then I want to claim that so let's say suppose you have a set of messages, I'll call them R, that satisfy the BP equations. Okay, then I can, then there exists a Gibbs measure mu R that I can write as, I'm going to write its probability on sigma A, xa. So there'll be some normalizing constant and product. So xu. So just the spin system on A. XV, these are U and V and A. And now I need something for the boundary condition. So we have our set A. What is the effect of the boundary? Well, it's going to be given by these belief propagation messages. So it's the W in partial A, W next to U, and in A. So I've just sum over xw. So summing over all the possibilities for each boundary vertex here. So over xw. And then psi of xw x xu, and then times r of the message from w to u of xw. So this is sort of saying that, okay, if we removed A from the graph, each of these vertices would have probabilities given, or marginal probabilities given by these BP messages R, and then we calculate the effect of putting A back in the graph. And and so if we have a solution of these BP messages, this will give us we'll construct this measure, and one can verify that this is indeed a Gibbs measure. So if we can find more than one solution of these BP equations, then there are infinitely many. Well, okay, that will be true. Then there will be more than one Gibbs measure, and because actually every mixture of Gibbs measures is a Gibbs measure, there'll be infinitely many as well in a sort of trivial way. Okay, but now.
Can all Gibbs measures be found this way?
No, no, because all extremal Gibbs measures can be found this way.
Plus mixtures. But
Yeah.
every extremal one can be found there.
Yes. Yeah. Yeah. So if you have a mixture of two Gibbs measures, you may not you in general will not be able to write it like this. Although, but you can have one's non-extremal Gibbs measures that are mixtures, which can be written like this too. So, so it's not a if and only if. Okay. Okay. But it, yeah. But they'll always, but there are particularly simple kinds of these fixed points of BP messages, at least if let's say we're talking about a random deregular graph. Then I can look for an R such that BP of, let's say, d minus 1, I'll just write times d minus 1 to mean d minus 1 copies of R equals R. So this is when it's regular, this is just the d minus 1 incoming vertices. And we can ask, can we find such an R that satisfies this? And I'll call these, I think in the notes I called them translation invariant fixed points, because they're just the same message everywhere. And you can always find at least one of these by the Brouwer fixed point theorem. So there always exists at least one of these nice set of BP messages where the messages are equal everywhere, and so then you get a Gibbs measure which is translation invariant. So it looks the same at every vertex. So there always exists at least one. So if we look at say the hardcore model and the Ising model, in this case, and we just want to find an R that's fixed, well, we'd have sort of R1 equals lambda. Sort of the 0 value is 1 minus the 1 value. Oh, sorry, that should be minus 1. So we just need to find a now a solution to this equation of one variable, and this is a decreasing function of r, so there'll be exactly one fixed point. So this is one fixed point. In the Ising model case, I'll get m equals, okay. Let's say r equals over the same thing plus, oh, and not a product, but just this to the power of d minus 1 plus the same thing, except switching the signs. D minus 1. Okay. This, you can check, is an increasing function in R now, so it could have more than one solution. It's when R equals a half, so you're symmetric between plus and minus, then then these two are just equal and you just get a half. So R equals a half is the solution for any value of beta. Okay, but so let me draw the picture of what this graph looks like. So this is R. There'll be a sort of symmetry around 1/2. So when d minus 1 tangent of beta is less than or equal to 1, the curve, this function will look something like this. It will, be equal to, so R will be equal to BP of R exactly at a half, and only at that point. On the other hand, when d minus 1 tangent of beta is greater than 1, the function will look like this, and you'll get 3 fixed points. So R plus greater than a half, 1/2, and R minus, which will be less than a half, and by symmetry, R plus and R minus will add up to 1. Okay, and so for each of these solutions, they each correspond to a solution of the BP equations, so they each correspond to a sort of translation invariant Gibbs measure. And how can you sort of realize these Gibbs measures as sort of the limiting procedure? Okay. Yeah.
R equals what, a half? What's the mean? You have halves everywhere, so is that like a uniform measure? Or?
Yeah. So this would be like R of plus 1. So it means that the probability of seeing a plus 1 is a half, and the probability of seeing a minus 1 is also a half.
But there are correlations between them.
I mean, just like the marginal at each vertex is equally likely to be plus or minus. So it'll just be symmetric between the two. And maybe I can sort of say how so we have 3 Gibbs measures, mu plus, mu minus, and mu free, which is not the same free as Ramon will talk about. But so the plus measure you get by taking all pluses as your boundary condition at level n, and then taking n to infinity. and this is sort of the most plus Gibbs measure you can take, because essentially, if I take some distant boundary condition, since the VP equations for the Ising models are increasing as a function, the bigger the plus value you have as, or the bigger value of m plus you have as the input, the bigger m plus you get as an output. I mean, at least when beta is positive, then having all pluses as your boundary condition is the boundary condition that makes the messages you get as big as possible. And then as you let the distance from the root tend to infinity, all of the messages will converge to R plus. Similarly, if you set them all to be minus, they'd all converge to R minus. If you set sort of the free boundary condition, which sort of says, actually we'll pretend that there's no vertices outside of this, then it's, first of all, it will be symmetric between plus and minus. And the measure that you get will be, all of the R's will be a half, and you'll get the free measure.
I have a question.
Yeah.
Because beta C, the critical data in which this transition occurs, a priori, you only have an inequality between this beta C and the real beta C for the Ising phase transition, because you don't, a priori, you don't know. So this transition is only for translational invariant Gibbs measure, right? So how do you rule out the case where, say, you take half of the plus and half of the minus for the boundary condition?
Okay, so in terms of the real beta C, I think there's different ways of interpreting that, but like one way is to sort of interpret it as, what is the boundary condition, for what values of beta can a distant boundary condition affect the root? Or is that?
I was thinking about the existence of different Gibbs measures.
Oh, okay, yeah. So when do you have a unique Gibbs measure or not? Well, if you're going to have, so any Gibbs measure can be realized by taking a random boundary condition or a sequence of those. Because you just take the random distribution you take is just to take the boundary condition according to that Gibbs measure. Okay, so so suppose we take a really, okay, so suppose some boundary condition, okay, let me say this. Suppose we're in this regime, and we take some really distant boundary condition. Then it should be a random boundary condition, but I can think of that as a mixture of deterministic boundary conditions. So it's enough to show that for a deterministic boundary condition a long way away, it doesn't affect what's happening at the root. Well, for any boundary condition I put here, it will be some combination of pluses and minuses. If I want to maximize the sort of m plus on some message up here, the best thing to take is all of these being plus, because the BP messages are increasing in the m's. But if I take all of them as plus, then I'll just get the probability according to the plus measure, which will converge to 1/2 if we're in this regime. And similarly, so all the messages sort of close to the root are sort of at most 1/2 plus epsilon, and they're all at least 1/2 minus epsilon. And as you let the boundary tend to infinity, they'll all converge to 1/2. So in this d minus 1 tangent beta less than or equal to 1 regime, there's just a unique Gibbs measure.
How do you deduce this from the marginals? I mean, it doesn't mean that the correlations between these things are the same. It seems it gives very, for example, it could be that mu f is 1/2 mu plus plus 1/2 mu minus or not, right? It's not clear from this computation. Also in that position.
So if I want to understand the joint distribution, say in the top k levels, I'll call this A. then what I would do is work out what all the sort of incoming messages from the boundary of A into A is. And if all of those messages are converging to a half, then I can sort of explicitly I can just write down the formula for this, and it will be the one corresponding to the free measure.
So for uniqueness, it's clear, right? But for UF, it's not clear here. Whether UF, for example, is 1/2 U plus plus 1/2 U minus, or whether UF is something completely different.
Right. Yes, and it is something completely different. Yeah. So, how much time do I have? Okay. In the 2 minutes left, I will describe give you another way of describing these measures, which is often much more useful, which is that we can think of them as a sort of broadcast or sort of Markov model. So basically, any translation invariant fixed point, I can construct the measure according to the following recipe. I pick rho according to its marginal that I calculate that this will be BP of R times D, because there's D incoming messages. And then as I go along any ray in the tree, the values along that will be a Markov chain. And the transition probabilities along the Markov chain will be, okay, if U plus is the parent of U, then the probability of sigma U equals Y given sigma U plus equals X. Well, this is just sort of one edge in the tree, but I know that there's a message R going this way and a message R going this way, except I fixed this one to be X. So it will be equal to some normalizing constant times psi of X Y times R of Y. And this normalizing constant just to make these add up to 1. So you first construct the root according to its marginal, and then each of its children you choose independently according to these transition probabilities, and then each of their children you choose according to their transition probabilities. And so one way of seeing that mu free is not a mixture of these two is that the Markov chains have different transition probabilities. And so they, on the infinite tree, they're singular. Okay, but I'm out of time now, so we should go to lunch. And then so this was on trees. We'll start working with these on random graphs tomorrow. Okay.